All right. Next thing we're going to talk about is called precipitation reactions. And a precipitation reaction is just a chemical reaction that produces a precipitate. Okay? And so when we're looking at that, all we are looking for is, something that makes a precipitate. And so then, what is a precipitate? Well, a precipitate is an insoluble solid that forms in an aqueous solution. Okay, and so we take that precipitate, we take these two things together, we pour them together in a container, poof, we get a solid that drops to the bottom. Okay, we have previously talked about this as double replacement reactions. Okay, so this is where we talked about this in years past, was a double replacement reaction. And if you remember that, we had the little formula where we had AB plus CD made. I'll just write it. So AB plus CD makes AD plus CB. That was the generalized equation that we used to explain what a precipitation reaction was. Oh, I'm hooked on a thing. Oh no. There we go. Better. Oops. Sorry. All right. That's what we call them. Okay, so here's an example of one that I think I've shown this one in the past, but we'll see. So lead nitrate plus potassium iodide, so 2Ki, and they're both going to be innocuous. So to be more correct, I should write that for you so that you see it. You're going to make 2 potassium nitrate, KNO3, and that's going to be aqueous, plus lead iodide, PbI2, and that'll be a solid. Okay, this reaction is really kind of cool because lead iodide is a brilliant yellow color, and it's just neat to see. So, okay, now, how do we know this happens? Well, we have to use our solubility rules. So we use our solubility rules to figure out what is what, to determine which solid will form. Okay, and so we have those yet, but we have to use our solubility rules to make sure that we understand what's going on. And so that's how this goes. So let me talk about those solubility rules, those guidelines, and we'll get to that in just a second. So if we're going to talk about our solubility guidelines, there's some basic rules. You guys have the solubility rules that you've been given in class, but the basic guidelines that we're going to use are the same. And so here we go. Just got yellow goo all over. Better. Okay, so here are those guidelines. So we have soluble ionics. So soluble ionic compounds. So these are going to be compounds that will contain, and there will be some important exceptions, all right? And you guys remember that too from using solubility rules in the past, okay? So if it contains nitrate ion, NO3 with a -1 charge, there are no exceptions. Okay, if it's got a nitrate ion in it, it's soluble. There's nothing you need to worry about with that case. Okay, if it has the acetate ion, CH3COO, with a -1 charge, that's acetic acids minus an H+, there are no exceptions. That will always be aqueous. Okay, if it's chloride ion, Cl with a -1 charge, the only time that there's an exception with that is going to be compounds of silver, so Ag plus 1, mercury, Hg2 plus 2, and lead. Those are the only three things that will make chloride ion into a solid. Okay. Bromine, it's got a -1 charge. It's going to have the same exceptions. So that's something to think about. Iodine, if it's got the iodide ion in it, it's the same thing, same exceptions. And then the only other one that we're going to add to this is sulfate, SO4 with a 2-. Now, sulfate is always aqueous unless it is combined with, so its exceptions are compounds of strontium, so Sr2+, mercury, 2+, so that's the same, barium, 2+, so that's new, and lead again. Okay, and so those are our aqueous situations. So these ions are usually aqueous unless they've got these exceptions that makes them solid. Okay, so then just a second we'll talk about our inaqueous compounds. Okay, so now we're going to talk about insoluble ionic compounds and their exceptions. Okay, so compounds that contain the sulfide ion, S2-, are always insoluble. That means they don't break apart and form aqueous solutions. They're just insoluble solids unless it is a compound of ammonium, NH4+, the alkali metal cations, and calcium 2+, strontium 2+, and barium 2+. Okay. Carbonate, CO3 2-. So carbonate are always insoluble solids unless, and we're looking at compounds of NH4, so NH4+ compounds, and the alkali metal cations. The alkali metal cations tend to make everybody want to dissolve in solution. So that's kind of what they do. Phosphate, PO4 with a 3- charge. This is the same as above. Okay, so ammonium compounds, alkali metal cations will make soluble compounds. And then hydroxides, OH with a -1 charge, are exactly the same as above, make them soluble aqueous compounds, plus calcium with a 2+ charge, strontium with a 2+ charge, and barium with a 2+ charge. Okay, now unfortunately for you guys, you kind of need to commit this to memory. Okay, the AP test is such that you're going to have it memorized, otherwise it's just the way it is. So try and work through these. The more of these you do, the more you work through, the more you work through them, the better you are at them, and the less you need your solubility rules. So there we go. Now, we called them double replacement reactions. Universally, though, there's a different name for them, and they are known as metathesis or metathesis reactions. Okay, and that comes from a Greek phrase meaning, what does it mean? To transpose. So they're called exchange reactions. And it's Greek, meaning to transpose. At least that's where it came from. Okay, and so that's a little high, I'm sorry. Hopefully it'll be all right. Now, before we do any of these other things, remember the holdup last year was making sure that your equations were done correctly. Okay, so make sure that your formulas are right. before you do anything, because otherwise you're going to drive yourself batty and you're going to just spend a lot of time at it, and we don't want to do that. Okay? Now, as you remember, we do have something that we would call a spectator ion, and these were things that didn't actually change. Okay? The analogy that we talked about last year in class was, if Mr. Burnett, me, is a spectator at a basketball game, I'm not going to change the outcome of the game on the floor. It's just whether I'm there in the stands or not, it doesn't matter. Nobody on the floor is going to play better because I'm there. So I'm not participating, I'm just watching. Okay, and so a spectator ion, these are ions in solution that don't chemically react. And because they don't chemically react, they don't do anything in the reaction. They're just there. And so what that allows us to do is that allows us to take those things out of our solution to make sure that we can just work through it and do what we got to do and don't worry about it. Okay? And so these spectator ions, they give rise to what we call net ionic equations. You remember those? I hope you do. Okay, and what we're doing with the net ionic equation is we're just breaking down the chemical reaction into what actually changes, and we're only talking about what changes. Okay, so we're going to go back to our lead iodide reaction that we had. Okay, and so here we go. Lead nitrate aqueous plus potassium iodide 2Ki aqueous is going to make lead iodide PbI2. This is our yellow solid, plus 2KNO3 aqueous. Okay? This is a molecular equation, because it has everything written down, and the molecular equation tells us what's changing, or just, it's everybody. It's the whole equation, so it's all pieces written as compounds. Now, sometimes, though, molecular equations are slightly disingenuous, because this KNO3, you recall from last year, that lives as an aqueous solution. So the potassium nitrate breaks apart and doesn't really live as a solid compound, as a compound hanging out together. Those pieces are going to break off, and they're going to be their own little thing. Okay, and so when we do that, we break this apart into what we call a total ionic solution. Okay? So total ionic equation. Sorry, I used the word solution. And so a total ionic equation, what it does is it just writes all the pieces that are there so that we have all of them. And so in this case, lead nitrate is going to break apart into a Pb2 plus in the aqueous phase. My two nitrates are going to, my nitrates here are going to break apart into 2NO3 with a minus charge, also in the aqueous phase. My potassium iodide is going to break apart into 2K plus in the aqueous phase, and my iodine is going to be 2I minus in the aqueous phase. All of that stuff together is going to yield what's over here. So we're going to have lead iodide, PbI2, as a solid. Now that doesn't break apart because it's an insoluble solid. It's going to sink to the bottom of the container. We're going to have left, we're going to have K plus, we're going to have two K pluses. Boy, that got ugly. Sorry. We're going to have two K pluses in the aqueous phase, plus two nitrates left in the aqueous phase, 2NO3 minus, and those are aqueous as well. Now, if we look at a total ionic equation, now we see things that are the same on both sides. And just like in math class, if you see things that are the same on both sides in a chemical reaction, we can just knock them out because they don't change. They're just there. They just do the same thing. So 2NO3 minus in the aqueous phase, 2NO3 minus in the aqueous phase, I can cancel both of them out. So that one's gone. Okay. 2K plus in the aqueous phase, 2K plus in the aqueous phase. They don't do anything. They don't change. They can come out of my chemical reaction. And so what's left is lead, Pb2 plus aqueous, plus 2I minus aqueous makes PbI2 as a solid. And so what we're going to do is I'm going to show you what that looks like here, and we'll rewrite some of that. And sorry, you're going to watch me erase, but whatever, it's fine. You'll get over it, right? So when we do this, what we have left is the net ionic equation. All right, and so the net ionic equation is what's left when we cancel out spectator ions. And so it is what's left behind after canceling spectator ions. And I'm going to put that in quotes, but spectator ions. Really what's going on is this is what actually changes. Okay. And so in this case, we're going to take our total ionic equation here, and we're going to just take and rewrite the parts that are left to write what actually happens. And in this case, it's Pb2 plus in the aqueous phase plus 2I minus in the aqueous phase. It's going to make PbI2 as a solid. Okay, so that's how we end up doing that. And that is really all that I wanted to talk about in this section. And so we're going to be done, and thanks again. Talk to you later. Bye.